Well, hello, AP Physics students. One more assignment to go here in Chapter 4, and I thought we'd just make it a good one here. So we're going to help you get started on problem 64 here, which this is a great problem because it's kind of got elements of almost everything we've done so far in this chapter. And as you know, physicists like to combine multiple problems into the same problem to really get at that problem-solving strategy. So let's go ahead and dive in here. So I have an inclined plane, and I have two masses attached by a very light, massless string, frictionless pulley, right? And I've got mass M1 and M2. And in part A, they say, you know, if M1 starts moving downwards, what would the acceleration of the system be? So we have connected objects here, we have inclined planes, we even have some friction between M1 and the plane here, and oh, this is good stuff. Well, let's go ahead and start in here, as we would any problem, by drawing in our free body diagram, okay? So obviously we have the weight here of M2, right, and that would be M2G. We have some tension force pulling up here. We don't really know what that force is. And then we know since this string is connected to both weights, I must have an equal tension force T here, and that's not a very good arrow, right? So this T and this T must be the same. Of course, M1 has a weight, right? And that would be M1G. Since M1 is on a surface, there is a normal force there, okay? And then we are told that the system is in motion, and that the system is in motion going in this direction here. So if M1 is sliding up this way, then our force of kinetic friction must be trying to oppose that motion going down this way. Furthermore, before we get started here, if we wanted to, we could break this force M1G, this weight, up into components parallel to the ramp and perpendicular. So if we did our triangle trig here, we would see that this would be M1G sine theta, the component of the weight going down the ramp here, and this component, the component of the weight perpendicular, would be M1G cosine theta, right there. All right. So that is a lot of forces going on there, and we're probably going to have to take all of them into account. So in part A, it says, what's the acceleration of these two blocks? What's the acceleration of these two blocks, assuming that M2 is moving down, all right? So we're going to define a coordinate system here, and I'm going to kind of define my coordinate system like this, okay? This direction here, I know this is crazy, this is the minus x direction, this is the plus x direction. This is the plus x direction. Mr. Kirsten, how can you define a coordinate system that's got a curve in it? What's going on? Well, since these two boxes are connected by a taut string, we know they're either both going to go this way, right? Or they would have to both go the other way, right? So either this one's going up and this one's going down, or that one's going up and that one's going down. And since you have a connected system like that, this is really a one-dimensional problem. So I can think about it kind of like that. So I'm going to say that my acceleration in the x direction, because that's what I want to know, is equal to the sum of all forces in that x direction divided by the total mass of the objects there. And again, since I have two masses here, but the masses are connected, I can almost think of them as like one object, one big mass. All right? Okay, Well, what are all of the forces? Well, before we get into that, let's do this first. What is the total mass of my system? The total mass of my system would just be m1 plus m2, right? And notice here, I'm going to stick with variables here until I get to the very end before I start plugging in numbers, all right? Okay, well, what's the sum of all forces then? Well, there's a lot of forces acting on this system. I've got the weight of M2 pulling down this way, right? I've got this tension force, and that tension force is going in what I'm calling the negative x direction, so I'm going to call that negative T. I've got this tension force here going in the plus T direction, all right? I've got friction, and friction I'm just going to call for right now F sub k, right? And the force of friction we know would be mu times the normal force, right? And then I've got the component of weight going in the minus x direction. So I'm going to call that minus m1g sine theta. Okay? Now, Mr. Kirsten, you haven't taken into account the normal force and m1g cosine theta, the component of the weight perpendicular to the ramp here. Well, those two forces are essentially canceling each other out, okay? So I don't have to take those into consideration here in my calculating, all right? Okay, well, I think that's all my forces. Let's see if I can't do some simplifying here. Now, I do know that M1 equals M2, so I'm just going to call M1 and M2 just M, all right? I can simplify things here, all right? So let's simplify. I'm going to get this to be mg. The two t's cancel out here. For my friction force, all right, let's see if I can't simplify that. That's mu times the normal force. Well, what's the normal force equal to? Well, that would be equal in magnitude but opposite in direction to this perpendicular component of the weight. So that would be mu mg cosine theta, since that's what the normal force would be equal to, right? So this would be minus mu mg cosine theta, and then we have our minus mg sine theta, okay? And this is over m plus m, right? Well, we're almost there. I think we just have to do some simplifying here. AX would be equal to, I can factor out an mg out of everything here. And this would be 1 minus mu cosine theta minus sine theta divided by 2m. And my m's would cancel out here. And really, oops, I'm going off the screen here. So really, when we simplify this, this is just going to be equal to g, which is 9.8, divided by 2 times 1 minus mu, which is 0.15, cosine 25 minus sine 25 degrees. Okay? And if I plug that all into my trusty calculator, I will get an acceleration here in this direction here of plus 2.2 meters per second squared. So this would be the acceleration of both block 1 and block 2, either moving down like this or up the ramp like this in the positive x direction, as I've drawn it here. Okay? All right, well, there is a part B to this, physicists, and I think they want you to find the smallest mu k that you could to have the acceleration of the system be 0. So I'm going to let you do that, tackle that on your own, and since I'm running out of time here, and the only thing I have left here for you then is the joke of the day, all right? Here we go. It's a one-liner, so think fast. Here you go. So when I found out that my toaster wasn't waterproofed, I was shocked. Get it? Shocked. Waterproof. All right. Nice work, AP Physics students. Finish up part B there, and we will see you tomorrow.